Hello, statics class. This first video I'm going to put together, I'm just going to cover sections 1.1 through 1.6 in the textbook. It's not necessary, I think, to go into as much detail on the first day of class into some of these sections, because I would rather emphasize section 2.1, which is where the homework is going to be based on. But it's good to get some of this material out of the way, just a refresher for many of these things. But I do want to give it some emphasis. So I'm going to make it into a video. So if you do feel like, boy, I really don't feel comfortable with some of the stuff, Dr. Deal went over it way too fast. So I'm going to instead refer you to this video. Right, to try to make that compromise, trying to be efficient in class and not bore you too much, or hardly at all. I don't want to bore you at all. So here you go. Let's go through sections 1.1 and 1.6 and try to be efficient about it. All right, so the bottom line up front, I try to have this bottom line up front type of thing, and this is really for section 2.1, but you'll see this in class quite often, bottom line up front. I'm just trying to say, what is the gist? What is it I want to get out of this class? And I'll tell you about this when class starts. But the idea that we want to have, this is the main topic of the day, is that we have parallelograms and triangles that we can use with our vectors, right? If we have two known vectors, P and Q, the resultant of those is the addition of P plus Q. You could think of if, like, I'm pushing on a car, or let's say I'm pushing on some like a chair, right? So a swivel chair that can move in any direction. A car just wants to go in the direction the wheels are going. But let's say I'm pushing somebody who's sitting on a desk chair and they're rolling, and then somebody else comes and they're pushing from another direction. Well, together, the direction and the amount of effort we're putting into it, right? The forces, which have a magnitude and direction, they're going to end up sending that chair in a different direction. They're going to combine together. And the total amount of force is going to be the resultant. So it's going to be P plus Q. And we could call it R is the resultant. Right? And there's two ways that we could do this graphically. We could either make a parallelogram where we make a line that's parallel to P and a line that's parallel to Q, and then we draw a line that connects the two, or we can add them. And when we add and create a triangle, and we use triangles, we go, convention is nose to tail for the things that we add, and for the resultants goes tail, tail, nose to nose. And you could do it either way. You could swap them out, right? So you could go from the nose of Q to the tail of P, and then you go from the tail of Q to the nose of P and you could see that P and Q end up being the same thing. So we could do this either way, either parallelograms or using triangles. And this is graphically, but we can also, with the triangle method is kind of preferred on one level, because we could actually find, instead of just relying on measuring things graphically, we can also get the solution using law of sines, law of cosines, and the trigonometry, so that we're able to find actual magnitudes and angles accurately. But that's the bottom line for class number 1. The things that we're going to, the takeaway. But this is like something that you'll see throughout the semester. So I'm going to do this again in class, probably about the same amount. I don't know exactly. I'll say the exact same thing. But this is like the bottom line up front. It's the beginning of class to tell you this is what we're going to learn today, so that then we can start going into more details. And so I think we learn in stages. So that's my technique, is to tell you the bottom line and then to start teaching the whole thing fresh. But what I want to tell you about the course, and this again, once again, this is stuff that you will be seeing in class 1. To give you an idea, we're going to break the chapter, break the book, go through chapters 2, 3, 4. We will skip 5 and then cover chapter 6, because a lot of these have the same things in common. Then we'll go to and skip to chapter 8. Right? And we're not going to do chapter 7 at all. And these are going to be all of this stuff right there. That's pretty much where the second exam is going to take place. And then for the last material is going to go back to chapter 5 and then do chapter 9. And they're very closely related, chapters 5 and chapter 9. They call them distributed forces, the title, but it's really like finding centroids. And then chapter 9 is moment of inertia. And those two topics are very, very connected to each other. And they're going to be useful in mechanics of materials and in dynamics. So that's, we figure we lump them together. But that's our game plan. So I think in any class we want to have this like introduction chapter, just to try to give us like the big picture of what's happening. And you ask the question, what is mechanics? And you could read this yourself. But it describes and predicts the condition of rest or motion of bodies, right? So statics and dynamics make up mechanics, right? It's how things move and the interaction of forces with rigid bodies, and it also includes mechanics of materials, right? Which we'll also cover in second half of your sophomore year. So all of these things together are mechanics, how things move, and the forces and the interaction with bodies and that kind of thing. Some fundamental concepts. The position of a point can be defined quite often. We use a vector, a position vector, to define the location in space. And we also have a coordinate system that and a number of different coordinate systems and an origin. And a lot of these things are kind of arbitrary, right? The coordinate system that we choose might seem arbitrary. A lot of times there's a convenience to picking a different type of coordinate system. Quite often, the most common for us, we're going to use Cartesian coordinates, but you'll see there's also cylindrical coordinates and spherical coordinates. In 2 dimensions, we call those polar coordinates, and sometimes we call them normal and tangential coordinates. But you'll see all that in dynamics. But we want to first define where a point's located. We also want to discuss time when to have a definition of when something begins and when something ends. We also want to have the mass of an object, right? That's different from its weight, right? Because it's related by the acceleration of gravity. And gravity isn't the same everywhere. So mass instead is going to be equal to weight divided by the acceleration of gravity at standard Earth conditions. We usually use 9.81 meters per second squared, or if you're American, 32.2 feet per second squared. And then we turn something into slugs in US units, but they're kilograms in SI units. But the mass of an object is really sort of its resistance to motion, right? So I think a lot of times I like to think of a van, right? If you had to push a van, it's really hard to get, you have to push, you lose a lot of force to get that van moving. But once it's moving, it's got inertia, right? And you have to start pushing the other direction to be able to slow that van down. Forces are that action that we use to exert on something. We could either be pushing or we could be pulling. And there are other kind of forces like gravity and magnets that can be away from an object but still causing a force on it. And a force is a vector, so it always has magnitude and direction. And we will deal with Newtonian mechanics. There are other kinds, I'm sure you learned in physics, where we have space, time, and mass. We think of these as absolute concepts, and we treat them as if they're independent of each other, even if we might recall stuff from physics class and find out that Einstein said that they're not. And I'm not saying he's wrong, obviously, but we want to stick with what Newton's approach to things, because we do want to solve problems and not overly complicate things. So we make those assumptions, and they hold up pretty well here on Mother Earth and in acceptably large but not too small scale of things. We say a particle is something that's so small that its actual dimensions don't really factor into the results, right? So it's all going to be relative to whatever we might be working with, but a particle is thought of as just being like, I have this little thing right here, right? This is a particle right here, and if it's just moving around or if it's just stationary, it doesn't matter. But like if we started like to spin this thing, now all of a sudden its shape might come into play, and in dynamics we would think about it as rigid bodies. But if it's so small and things that are working on it, the size and shape of the thing don't really matter. That's a particle. Rigid bodies, however, they're large enough and have a shape that's going to influence what the results are going to be. And for statics, that means that we end up using the sum of the moments. All right, and so that's things coming up. And once again, I'm making this way longer than it needs to be. I won't take this amount of time in class. I might not even cover some of this in class. I'm wondering if I might take away too much from the really important stuff. So that's section 2.1. So the principles, we use the parallelogram. I already kind of like talked about that in the bottom line up front, right? That two forces can be summed into one using a parallelogram. We also have the principle of transmissibility. Let me see, we're trying to force can be moved to a different location on a body as long as it maintains the same line of action. All right, so a line of action is, like if we have a force vector right here, the line of action is the line that's passing through the thing. So that's the definition there of the line of action. And so sometimes you might think of that as the sense of the vector. So it just says it won't matter as long as we maintain that same line of action where we're applying the force, whether for us a vector is a push or a pull. When it comes to just applying a vector to something, a force vector, the transmissibility means that. I don't think it's that big of a deal. Newton's three laws that we're going to care about in this class, we're going to care about the first and the third law, which the sum of all the forces is zero. When that happens, there's no acceleration, and vice versa. When there's no acceleration, then all the forces must equal to zero, right? Second law, that's the F equals ma. That's Newton's second law. I call it N2L when I refer to it in dynamics, but that means that the sum of the resultant forces is going to be equal to mass times acceleration. And then the third law, the forces are equal and opposite. So for every action, there's an equal and opposite reaction. We know about that, right? So if we push on something and it doesn't move, this thing is pushing back onto the finger, right? So this one is finger pushes on this thing pushes on the finger, right? So there's in between these two things, there's an equal and opposite force right here. It's going to be an important principle for us when we apply something called the FBD, which is not a bad idea to mention. The most important thing in statics, the thing you want to know for the rest of your life as an engineer, the all-important FBD. We will be covering that very, very soon, not today, or not on the first class, but FBD is the most important thing you will learn, I believe, as an engineer. Whether you be, I'm not sure that the electricals care so much about it, but the civils, mechanicals, and biomed, man, you guys, you need to know FBD and live it, love it. Newton law of gravity, that's a really interesting thing if you're going to start getting into the motion of planets and moons and spacecraft and that kind of thing, but we're not going to cover that. All right, system of units, kinetic units, length, time, mass, and force. These are like the basics that we need to have. These are the most basic of units. The last one here, force, is actually a derived thing. It's not really something we can actually measure. We could measure the effects of a force, like if we had a scale. The scales really has a spring in it, where it can have it could also be electrical things that can measure, and it's usually a change in resistance in the thing that's we're measuring. So it's one of these things that was kind of derived from the other things that you're measuring. The two system of units, we have the SI SI units, which we use meters, seconds, kilograms, and newtons. And if you ever want to try to convert, a newton is equal to a kilogram meter per second squared. Think F equals MA, right? Newton is the measure of a force. Kilogram is a measure of a mass, and meters per second squared is a measure of acceleration. If you have US units, they use feet, seconds, and this thing called slugs. That's to be sort of like to have something that's similar to kilograms. It's the measurement of mass in US units. And you could think of slugs as in sluggish. It's its resistance to motion. That's why they come up with slugs. And then finally, pounds is what we use for force, right? A lot of times we get confused. We think of weight of something and the mass of something being a thing. But if it's the weight, it's a pound. If it's a mass, it's a slug. And if you want to convert, the conversion is the pound is equal to a slug feet per second squared, right? Where F equals MA once again, right? Newton's second law is what we would use just to conceptually to think about those units. And this is out of the book. You'll see. I think it's really important that we check this out. Make a mention of this, that the method of solving things that they suggest is the SMART strategy, and they forced this acronym into place where we're going to have it's a SMART strategy. Well, the first thing is a strategy is when you read a problem, you want to try to break it down and look at it carefully. A lot of times this process for me is just redrawing the diagram of the problem. And by redrawing the diagram of the problem, I start thinking about what's going on. I write down what all the knowns are next to the thing. That's the first thing I do. And as I'm doing that, that's my process of starting to identify what is going on here. And then I read the objective, and I like to write down find, and then write down exactly what it is that we want to find. It could just be a variable that we want to find. And then by doing that, I start to find a strategy. I don't always know exactly the strategy, but I kind of go, well, okay, hey, I could find this, and then I could also find that. And then maybe that light bulb is going to turn on. So that's what happens when we're solving problems. It's especially something important to try to think of in terms of when you take dynamics. Dynamics has lots of problems where they're much more difficult, and you have to try to find this strategy and weave your way through into getting a solution. Modeling, that's also something we want to, for us, one of the most important things is, well, there it is again right there, the FBD. We want to create a model to like replicate what's actually going on. So even though we might have drawn something up here when we were writing down what the problem was, right, to rewrite down what the problem statement is, we want to draw an FBD. We'll define what those are, but those are like taking a part of the body and isolating it. All right. And so that's going to be the model of the thing. So that's the idea of the model. And then the analysis is we apply the fundamental principles, that's going to be the sum for us in statics, the sum of the force is equal to 0. The sum of the moments is equal to 0. That's all. And so we use the math and so forth, with these, analysis and these fundamental principles. And that includes geometry and trigonometry and algebra and calculus to try to, solve the things. And so we come up with a, solution in the analysis, but that's really, so a lot of times that's the thing that people jump to and the only thing that they do. But we want to try to consider the other, the S and the M. We get to the A part of the thing. And then we also want to reflect on and think about the answer, right? Does it make sense? Right? And if it doesn't make sense, we could start to pick it apart and try to think, okay, where could we have gone wrong? Maybe is there another method to apply to this? And maybe if we use that other method, we'd be able to come up with a solution. Numerical accuracy, I probably will harp on this more than anything else during class, and that's the idea of significant figures. My directive to you is to use no less than 4 sig figs for all calculations. Do not round down. You can round down at the very end, but when you give an answer, give me 3 or 4, right? And some people insist on 3. I say 3 or 4, that's fine, because there's some conditions where 4 is more appropriate. I'll just tell you the conditions. When the first number of your sig figs is 1, then you should use 4 sig figs. If it's something else like 2, if it's 2.8745, then you only want to 2.88, right? Because I just said there was 5 right after the 7. I think I did. I don't remember what number I said. But anyway, you would do 3 sig figs. But I say go ahead and go 4 all the time. I don't care. Just don't give me 5. Don't give me 6. Don't give me 2. I want 3 or 4. But when you're doing, this is even as important as the answer as to be limited to 3 to 4 sig figs. Don't ever drop below 4 sig figs for in-between steps. That will throw off your accuracy. But if you stay to 4 sig figs, you should be good. If you're doing it on a calculator, a lot of times then it's just already in the memory of the calculator, so you don't need to round down. I mean, it's somewhere hidden in the calculator. It's probably hundreds of digits long. I used to know how many it was. Yeah, the accuracy will be perfectly fine. But if you've written down a number on your piece of paper and you're going to have to re-enter it into your calculator, don't round down at that point. That's the important thing. And okay, so this is where chapter 2 comes in. One last thing. So this video is ending here. One last thing I would tell you, let's see, we'll discard all this stuff right here. And I want to direct you to a part of the book right here. So this is called Solving Problems on Your Own. And I really recommend, if you're struggling with the course, to take a second before you give up and throw your hands up in the air and go ask someone down the hall, or go to the tutor, or come to me, or go to Chegg. Don't go to Chegg. Before you go to do all those links, go to Solving Problems on Your Own. Right? Check this out and start thinking about the things that it tells you right here. After every section, there is this section. After every section, there's this part called Solving Problems on Your Own. And read through this, and it'll give you sort of this guidance to help you organize your thoughts. Quite often, that's the thing that is the Achilles heel of we engineers while we're taking classes, is that our thoughts become chaotic, and we need to organize them in order to become problem solvers. So this is one of the usefulnesses of this textbook, I think, is solving problems on your own. And so that's today's video. Let's see, how long did I take into the thing? 22 minutes. I think it was worthwhile. I'm not sure how many of you will watch it. Maybe I should look later after the next week, see how useful this video was. I'm going to make some other videos for the rest of the section. I'm not going to do this for every class, because you do need to come to class. Otherwise, if I just made videos, all you would need to do is just watch the videos. But I will make many videos and link to other things to help support you in this endeavor. And you can always come to me. So thanks a lot, and hope to see you in class very soon.